My name is Ilham binti Abdullah, a Bachelor in Computer Science student. Welcome to my final year project presentation today entitled Image Classification of Aedes Mosquitoes Using Transfer Learning. My supervisor is Dr. Pradeep Isawasan, and without further ado, let's start with the presentation. Is introduction, which is the project background. There are over 3,000 species of mosquitoes all over the world, but the members of three Anopheles mosquitoes, Culex mosquitoes, and Aedes mosquitoes are responsible for the spread of many diseases. Mosquito-borne diseases caused by Aedes mosquitoes alone, such as dengue, chikungunya, and Zika virus, has affected a great number of people worldwide. Machine learning, it has solved many problems, and the advancements of machine learning has provided many solutions for various problems in all fields, including the study of health, agriculture, autonomous vehicle, entomology, and many more. The necessity and applications of image processing, specifically image classification, to solve real-world problems in recent years have increased over the years. So classification of objects is really complex, and that is where image classification with the help of machine learning comes in very helpful in the computer vision field in digital image analysis. So image classification can solve real-world problems and also help to solve complex objects. So next is convolutional neural network, specifically deep learning. Convolutional neural network, or CNN, is particularly an algorithm that has been constructed and refined with time in the progress of computer vision. With deep learning, CNN is most preferred because it performs better than other classifiers such as SVM and KNN, and this has been proven to give higher accuracies and better efficiency. So, since it is feed-forward and highly effective in decreasing the number of parameters without losing on the quality of the models. So for this project, we are doing image classification using transfer learning to classify the images of Aedes aegypti and also Aedes albopictus. This is our problem. So basically, major outbreaks of these diseases have been causing trouble to populations and overwhelmed the health systems in various countries since 1980s due to the diseases that these mosquitoes carries. This is according to Nile in 2014. So the identification and classification of the species is very demanded for entomological characterization in obtaining data and information regarding the mosquito's behavior. So currently there are several methods used to identify the species, which is first DNA barcoding, environmental DNA testing, and also real-time PCR or qPCR. Problems that comes with this conventional method of classifying species of Aedes mosquitoes. The first problem is the whole process of mosquitoes classification itself takes very long time, and it tends to be very difficult, as it is very difficult to identify species from around 3,500 different species of mosquitoes that present today. So there is a significant need for machine learning or deep learning application in order to make the process of classification easier and faster. And secondly, we are lack of surveillance and monitoring, especially in potential areas with low and sometimes high vector density for early detection of the presence of Aedes mosquitoes. So because this lack of surveillance and monitoring of the spreading of these Aedes mosquitoes, it is more difficult for us to combat this disease and combat this spread of the hatching of the Aedes mosquitoes, right? So to our this research aims to accomplish two objectives. which is first, we want to build and design classifier using transfer learning for Aedes aegypti and Aedes albopictus. And the second one, we want to investigate the performance of transfer learning method on Aedes aegypti and Aedes albopictus image classification model. So this project will focus on two species of Aedes adult mosquitoes, which is Aedes aegypti and also Aedes albopictus images, which the input data acquired in the dataset are 2D images, and the dataset consisting of 1,205 images are Aedes mosquitoes of both species. Is the significance of the study of entomology is considered to be a priority by the WHO to develop tools which will be applied to cut back or to reduce and maintain the mortality and forestall epidemics caused by mosquito-borne diseases worldwide. So we want to cut back and maintain mortality and forestall epidemics, and we want to enhance the investigation and monitoring in order to put a stop to this increasing number of dengue cases. And then we also want this image classification model to identify adult Aedes aegypti and Aedes albopictus to assist the work of entomologists, health workers, and many more, right? And lastly, it is vital for both the recognition of the vectors involved in diseases, transmissions, and the development of structured and methodical control strategies. Next is a literature review done for this. So globally, more than 1 million people are infected by these vector-borne diseases, and it includes more than 1 million people who die from it each year, including mosquito-borne diseases. So Aedes aegypti and Aedes albopictus both can carry this same disease, but they also carry different or transmit different kind of diseases. For Aedes aegypti, it can carry and transmit dengue, yellow fever, chikungunya, Zika virus, and West Nile virus. As for Aedes albopictus, it can carry and transmit dengue, chikungunya, and West Nile virus. So is the physical features differences that we will be detecting using our image classification model that will be built for this project. It will look into the presence and also absence of the white scale layer on thorax or a median of the Aedes mosquitoes. These will differentiate the species between Aedes aegypti and also Aedes albopictus. As you can see, for Aedes aegypti, it has the presence of white scale layer on its thorax, the two white scales, and as for Aedes albopictus, there is absence of the white scale layer. And then we also have the presence and also absence of white scales on clypeus. Okay. Next is the CNN in image classification convolutional neural network. In recent years, CNN have made many significant achievements, thus including object detection, classification and segmentation can be done with a single model architecture. So hence it is proven to be powerful as it is a generic class of models for many tasks. So it can automatically learn optimum features from a huge training data sets, and it also can classify images using modern deep learning methods that give higher accuracy than humans. So for transfer learning, which is a concept that will be used for this project, is the idea of overcoming the isolated learning paradigm and utilizing knowledge acquired from one task to solve related ones. So we use the pre-trained models to create a new model using the weights from the pre-trained model to improve the efficiency and the accuracy of the model that will classify the images of Aedes mosquitoes and Aedes mosquitoes, which are the Aedes albopictus and Aedes aegypti. So this figure that is shown here shows the difference between learning processes in conventional machine learning and the learning process of transfer learning, where conventional machine learning techniques start learning each task from scratch. On the other hand, transfer learning techniques uses the knowledge from previous tasks to transfer to a target task, and knowledge is not retained to transfer to any other model. This way, transfer learning is able to tackle the insufficient or well-labeled training data, which is very crucial issue in machine learning. Okay, so this is the comparisons of related works, so the past works that is related to the project that we are doing today. So we have project on Aedes larvae classification and detection, ALCD system, which classifies that determines and classify mosquito larvae using CNN and deep learning technique, which achieve the accuracy of 73%. We have the classification of mosquitoes to classify mosquitoes using CNN and data augmentation technique, which is 93%. And we have also a few other other works that use 3 types of deep classification methods, which achieve the accuracy of 95.5%, and also the last one is the one that uses as. So next, moving on to the methodology of our project. So this is a project framework for the project that has been designed and will be implemented throughout this project. The first one is planning, and then we have information gathering, implementation, result analysis, and documentation, which will be explained more in detail later. First step is planning. So the activities will be done in this stage is discussion that has been done in this stage was discussion with project supervisor, and I already determined the research area, defined the problem statement, identify the objective, scope, significance, and background of the study. And what we did was using online resources such as research papers, journals, and news article. And with that, I had been able to deliver project title, introduction, problem statement, and objectives. Also, the significance and expected outcomes of this project. And next we have information gathering. So for information gathering, the activities that is done is knowledge acquisition on Aedes mosquitoes classification related projects, and then we acquire knowledge on image classification techniques, the comparisons of performance using CNN and SVM, and then we review related projects and also construct a concept map. And with that, I had been able to deliver the literature review and chosen techniques and methods that will be used for the development of the project. Okay, so next we have implementation. The activities that we did was decide the research methodology model, and then we developed an image classification model for Aedes mosquitoes through coding, and then we do the model training while applying the transfer learning method and test the trained model, and we visualize the performance of each experiment that we did. So by using Google Colab and also Keras and TensorFlow libraries, we were able to deliver machine learning lifecycle model and also Aedes mosquitoes image classification model and the performance results. So this is the machine learning lifecycle, which is a cyclic process that acts as a guideline to build a machine learning project efficiently. So the cycle gives structure to several phases that involve in machine learning project development, that particularly this research to provide control in the development process. As we can see here, we have gathering data and then data preparation, analyze data, train model, test model, and performance. So we can see here more in detail. For gathering data, we will gather a data set of 1,205 205 images of Aedes aegypti and Aedes albopictus, and then for data preparation will be done data augmentation and analyze data to determine the best approach, and then we train model using 70% of the data set, and then we test the model using the testing data set, and we deploy, or we did performance. And then moving on to the next step is result analysis. So in this stage, we compare and analyze the performance results after implementing the transfer learning concept, and we evaluate and find the best performance, and we did analysis on that results. And with that, I would be able to deliver the results, findings, and discussion, where I prepare the documentation and gather all project details, discussion, and analysis. And with that, I was able to deliver the project dissertation. Okay, so next is the project design and implementation. As discussed previously, we have the project flow or the machine learning life cycle. So this is the project workflow for the deep learning model to classify images of Aedes mosquitoes, designed as the main guideline throughout the project development. Classification of Aedes mosquitoes using transfer learning project code implementation. It is actually a binary image classifier built to classify Aedes mosquitoes into Aegypti and Albopictus classes using MobileNet v2 and also VGG16 pre-trained model. So this is the environment that I use for the code implementation. Due to limited resources, especially in terms of hardware requirements, I use Google Colab, which is free as long as you own a Gmail account. It is actually an online cloud-based Jupyter Notebook environment that provides the ability for deep learning model training. So as you can see here, the Google Colab actually provides a CPU runtime with a memory of 13 gigabytes. And the next initial setup that I did was to import all the libraries necessary and will be needed for the whole project. And the most important ones are TensorFlow. The version that I use is 1.10.0, and also Keras 2.24 version. So with TensorFlow and Keras, I am able to use all the packages and the variables that comes along with the big libraries, and it is extensively used for deep learning projects. So then the next initial setup that I did was to mount Google Drive to access dataset, and since I'm using Google Colab, it is easier and faster if I store all my dataset in my Google Drive account and let Google Colab actually access my Google Drive. So with that, I wouldn't have to upload my dataset every time, and it would take a lot of time. I can do that actually, but I don't. So we use Google Drive for easy access. So here, when I have already mounted or connected my Google Drive to my Google Colab, I set the path for my training, validation, and testing Aedes dataset. There are actually 3 different folders in the Google Drive Google Drive folder, set for train, valid, and test. So here you can see the I link my Google Drive with the Aedes training folders to a path. This is for train path, valid path, and test path. And this is where I initialize the epochs number of 100 and batch size of 32, and this can be changed later on when according to the experiment that I'm doing. And then here comes the exploratory data analysis that I did. This is actually a part of data gathering step, where it is a process of the preparation that I do before starting the experiment. So in this process, the first step is taken is actually splitting the label data set separated by folders. I explained this just now, where I actually stored the images of the mosquitoes according to their class, and I divided them into 3 folders. The first folder is training with 70% of the whole data set, and then I separated 20% of the data for validation, and another 10%, the last 10% for testing data set. So this is where I check if all the classes are in their respective folders match, and I identify if there is any class imbalance in terms of the data set, the number of images and whatnot. So here I check if all classes match in the train path, in the training data set, and it matches Aegypti and Albopictus, also in valid path, and lastly is test path. Okay, and then I check the number of images in training and validation, and also testing data sets, how many of them, total number of images, and it is displayed here. Number of training images, there are 842. As I said just now, it is 70% of the whole data set, and then 240, which is 20% of the whole data set, and also 121 for testing images, which is 10% of the whole data set. Okay, so next is the step in the framework where I actually do data preparation. So in data preparation step, data pre-processing took place, and this is where I use image data generator that is provided by the Keras library just now, using keras.preprocessing library. So image data generator actually will import the data with labels easily into the model using the flow from directory method. So here I'm using the flow from directory method that is provided by image data generator of Keras processing library. And then the training, validation, and testing image data set that is mounted from Google Drive folders will be loaded into the image data generator to specify its path. Okay, so here I create a data generator or the train generator. I name them valid generator and test generator according to their type of data set. And using the .flow from directory, as I mentioned just now, I address them to this link in my Google Drive, and then I resize it to 224 by 224 as expected by the pre-trained models. Batch size equals to batch size that I initialize the first time initially, and then class mode is categorical, as we are doing a binary classifier. We are classifying into 2 types of classes. So this is what I did using the image data generator. So next, what I did was I did data augmentation here, where it is a real-time or runtime augmentation that is done as a technique to reduce the overfitting during training of the model, and this technique can prevent various forms of biases such as scale, background, and many more. So Here we can see that I implemented it. The images in training set are rotated randomly, ranging from 0 to 270 degrees. And yeah, as I said, each rotated image will be unique, and the image data generator class will allow random rotation on images by providing integer value in the rotation range argument. Okay, so next, other than that, I also did randomly flipping half of the images horizontally. This is one of the easiest augmentation techniques. It's a geometrical transformation augmentation technique that flips images randomly along the horizontal axis. So that is what I did. And the images will be generated after augmentation for the dataset on the fly while model is training later, since it is designed to provide real-time data augmentation. So basically, the image dataset original batch of images will go through data augmentation, and then the augmented batch of images will be used for the model training on using the DCNN model later. So next step is the model building. Okay, so here is where I actually define my hyperparameters for hyperparameter tuning, which is actually a big role in machine learning project development, because major hyperparameters will affect the whole model training in especially the model performance. So it is important to find the best parameters. So, for this project, I use manual tuning or the brute force method, using repeated experiments. So with manual tuning, there is no use of automation or library used during the parameters to replace and its value selection. It is only changed from time to time based on the current selection of parameters, and their scores are evaluated, and the best hyperparameters is used for this the whole experiments. So here you can see the setting of hyperparameters used for model training defined in the coding. And the first one is dropout rate, which is the regularization technique, which we can see how it was used later. And the learning rate is 0.01, batch size is set to 32, and epoch is set to 100. Therefore, hyperparameters set here. And then moving on to the next step is the model building. The creation of the model. So here is where we create and initialize a model for training, and this is where transfer learning method is applied. So the model is actually specified as a sequential, which is actually which actually means that it arranges all layers of the model in a sequence. So transfer learning is an approach that keeps the core pre-trained model intact. So here you can see we are using actually VGG16. We are importing or loading the model of the VGG16 train before, and then the weights, some of the weights or the base model, we call the pre-trained model as the base model. The base model weights are freeze or set to freeze, and we add some other layers on top of the base model. So that is how actually transfer learning works. So in order to ensure the pre-trained models work better for this project's classification problem, fine-tuning is done on the model. Fine-tuning is actually a technique used for transfer learning concept. So actually the pre-trained models weights are set to freeze, as I said just now, in order to stop them from changing during the training process. and the original classifier layers are also replaced with new layers. So these are the new layers that we add, and it is designed to suit the need of this classification problem especially. So yeah, we removed the model classifier on the top model classifier of the pre-trained model by setting it to false, and then we added a convolution block of caris.layers global average pooling 2D, and then dropout layer as the regularization technique to prevent the model from overfitting. And then there's a fully connected layer here, dense with 256 units on top of it, and it is activated by value activation function so that all negative values are not passed to the next layer, and fully connected layers named dense with 2 units on top of it is also added. 2 is because there are 2 classes to predict for the model, which are Aedes aegypti and Aedes albopictus, and it is activated by the softmax layer that will output the value between 0 and 1 based on the confidence of the model that which the class images belongs to. And yeah, that is it for the model creation. And then we print the model summary to see how it looks like. So it is actually just it looks just how we created it just now. And here you can see non-trainable parameters are 14 millions, right? This is actually due to the frozen weeks from the base model. So it is non-trainable. When we freeze it, then it becomes non-trainable. And then for trainable parameters, only left to 131,000 plus. Okay. So next we compile the model. The model that we created must be compiled using model.compile function, where Adam optimizer is used with the learning rate value that we have initialized previously, and also its loss function using categorical cross entropy because we are classifying 2 classes. And also the metrics that we use is accuracy that will print out the accuracy score later. Okay, so next is our model fitting. Model fitting is actually the model training. So once the model is compiled just now, the training of the model can start, and the model will start training for 100 epochs because we have set the values of epochs to 100. So we can see here that we use the train generator, which is actually the datasets that contains the training dataset, and also the validation dataset is stored in validation generator using the epoch of 100, and verbose too. Verbose is actually how this output is displayed here, and you can see the training starts from 1 until 100 epochs. Okay, so here it actually output the values of epoch number and duration in seconds, duration of the training, and then we have loss and accuracy score for training, loss and accuracy score for validation throughout the training process. Okay, so next we have so after the training has finished, we visualize the training and validation performance by generating visualization using the matplotlib.pyplot library. Okay, So we want to visualize the accuracy of the validations and also the loss of validation, accuracy for validation and training, and also loss for validation and training. So this is where we defined all the plotting for visualization. Next is testing model. Okay, so this is the final important step where the model testing process will tell how well the model trained earlier performs on data that it has never seen before, which is the data set that we have separated earlier, the 10% amount of data, which is 121. So it will actually see if the predictions will match the actual labels for the data that will be tested. So here we can see the predictions is equal to model.predict function. So we define a variable named predictions and assign the predict function, model.predict function, to have the model trained earlier. Make predictions on the test data set by passing the test generator data set. So to assist, so after it has done with the predictions, to assist in the process of evaluating the performance of predictions to see how well it performs in predicting the right or wrong classes or labels for the images given, we use a few performance metrics for the classifications. The first one is confusion matrix. The confusion matrix will be printed out and we'll see how many correct images are predicted by the model and how many wrong images are predicted by the model. And that way we can see how well it performs. And we also have the this is where we define the definition for confusion matrix. And then we also use accuracy score to actually see how well it performs. And it is actually an important evaluation of performance metric for model testing to see how well it performs, right? So this is for VGG16. The model that we created just now is for VGG16. It is the same with a MobileNet v2. This one is for MobileNet v2. The whole coding is just the same except for when we were loading the base model used for the model creation. So here in this code we load MobileNet v2, and then on the other hand in this code we load the pre-trained model of VGG16. So that is all. Thank you. Classification of Aedes mosquitoes using transfer learning project code implementation. It is actually a binary image classifier built to classify Aedes mosquitoes into Aegypti and Albopictus classes using MobileNet v2 and also VGG16 pre-trained model. So this is the environment that I use for the code implementation. Due to limited resources, especially in terms of hardware requirements, I use Google Colab, which is free as long as you own a Gmail account. It is actually an online cloud-based Jupyter Notebook environment that provides the ability for deep learning model training. So as you can see here, the Google Colab actually provides a CPU runtime with the memory of 13 gigabytes. And the next initial setup that I did was to import all the libraries necessary and will be needed for the whole project. And the most important ones are TensorFlow, The version that I use is 1.10.0 and also carries 2.24 version. So with TensorFlow and Keras, I am able to use all the packages and the variables that comes along with the big libraries, and it is extensively used for deep learning projects. So then the next initial setup that I did was to mount Google Drive to access dataset, and since I'm using Google Colab, it is easier and faster if I store all my dataset in my Google Drive account and let Google Colab actually access my Google Drive. So next is the results and findings for this experiment project. So here is the model performances result stored in this table right here, and we can see there is batch size 32 and 64. For each batch size, we have the the learning rate of 0.001 and 0.005, both for batch size 32 and 64. And these are the scores, the accuracy scores is percentage for MobileNet V2, and this is the accuracy scores for VGG16 model. So we can see here the best performing model is actually MobileNet V2 with accuracy score of 96.69%. It is the highest accuracy score overall, and it outperforms the use of pre-trained model of VGG16 in all combinations of hyperparameters used in the experiment. So okay, and then we have here is this figure right here is for MobileNet V2 training / validation visualization of graph from the training and validation step of the model before it was tested. And here is the VGG16 one. These demonstrate that the MobileNet V2 architecture produces good performance, as you can see here, between the efficiency and consistency of accuracy of results in terms of accuracy and loss during training and validation. As you can see here, this is within 100 epochs. Okay, MobileNet V2 is actually comparably thinner and more lightweight network due to fewer parameters compared to VGG16, which is very suitable for experiments with limited training samples. Referring to this project, we have limited samples due to limited data set samples. So theoretically, any deep CNN architecture can actually be used for this approach, and this is proven by how both models actually performs very well, because MobileNet V2 performs like higher than 90%, and also VGG16 also performs actually higher than 90% here. So it is considered to perform well for both models, even though that MobileNet V2 outperforms VGG16. And the application of fine-tuning in transfer learning concept is proven to improve the performance of model. So here we can also see that despite the fact that MobileNet V2 has highest accuracy score and it beats VGG16, there is actually a noticeable similarity that contributes as a major factor to the highest accuracy of both models. As we can see in the table previously, both MobileNet V2 and VGG16 actually obtained its highest accuracy score by using batch size 32 and learning rate of 0.001. And this demonstrated that a significant factor based on the results to achieve the best performing model, we can conclude that it is proven that hyperparameter tuning is very, very crucial in order to obtain high accuracy. So hyperparameters, specifically the learning rate and its batch size, has to carefully be decided since it affects majorly on the performance of the model. So, in conclusion to this project, it has designed a model framework that utilizes the concept of transfer learning by using pre-trained models to classify images of Aedes mosquitoes according to its species. Fine-tuning done based on the concept of transfer learning improves the model of performance significantly. The architecture is also evaluated based on the performance produced by experiments conducted using different combinations of hyperparameters and selected MobileNet v2 as the best performing model for this project's classifier model, which has achieved the highest accuracy. So the hyperparameter tuning done on all experiments also became a major factor to the performance of models tested, and explain how a deep learning model can be improved by applying different techniques. At the end of this project, the results obtained and discussions presented have proven that this experiment has successfully achieved the main objective, which are first to build and design a classifier using transfer learning concept for Aedes aegypti and Aedes albopictus. And secondly, the objective was to investigate the performance of transfer learning on Aedes aegypti and Aedes albopictus images. The next one is the project limitation. So the image classification of Aedes mosquitoes using transfer learning model architecture has already proven that it meets its objective and will be beneficial in the process of classifying images of Aedes aegypti and Aedes albopictus according to its species. However, there is a limitation. The first one is the data set used in this project are the images taken by a specific device and with the same background under the same lighting, which makes the appearances of the physical features of the mosquitoes in the image dataset consistent and not as challenging for the classifier to detect. And the second limitation is the model architecture of this project was trained only on two different species, which is Aedes mosquitoes aegypti and Aedes albopictus. So this model is limited to recognizing only these two set species, which means it is not familiar with other mosquito species present. This will impose as a constraint on the model's ability to predict other mosquito species correctly. So for future work, there are a few enhancements that could be done to further extend the benefits and utilization of this model architecture in order to help combat airborne diseases. So the first one is more data set can be gathered by expanding the collection of data sets across the world taken using different devices and various backgrounds and settings. The larger the dataset, the better the model will learn and performs in the future, and it can possibly be deployed as a system or a mobile application and be very, very useful for entomologists, health workers, and also can potentially be non-expert friendly. And secondly, we can implement different and more extensive and intensive techniques in order to further improve the performance of the model to classify mosquitoes images. So here are the references for this project. With that, I will end my presentation here. I would like to thank all and everyone that has directly or indirectly participated and contributed to this project. I would like to thank my supervisor, Dr. Pradip Visawasan, and I would like to thank all my lecturers, including Dr. Imran, for providing me guidance and also supervision throughout throughout the completion of this project. So with that, thank you for your time and attention. Take care and stay safe.